last lecture. I made something sound more complicated than it was. So I apologize if you just like a couple more minutes about this. So it was the part where I was talking about, how does the separation oracle work? Right, so we're applying the ellipsoid algorithm to this dual linear system. Okay, and at the end of the day, we know we're going to actually prove that this is infeasible. But it's the part of the proof where we're trying to argue, we're trying to implement the separation oracle. So the first thing I said was correct, which is just this last constraint. Okay, so remember the y. Okay, let's remember what everything is. All right, so at the very beginning, right, long ago, there are these real valuations that you care about, the VIs. You solved the linear probing relaxation for welfare maximization for the real valuations, the VIs. Y star was the best fractional solution for the original ones, the VIs. Okay, and for the rest of the proof, you're just taking the Y stars as targets, just as fixed given constants. Okay, and so in this dual system, the Z's are what are the decision variables. So you check this last constraint, and then obviously if this is violated, you can go ahead and return that. And then the claim is, if this last constraint is not violated, well then actually it's super easy to generate a violated constraint from this family. Okay, so that's the step that I made it sound way more complicated than it is. So to first order, here's how it would work. This assumes you're okay with like a randomized solution. So suppose this passes the test. This is actually true. So now what do? You just run randomized rounding from last week. Meaning, you scale down by a small factor, 1 minus epsilon factor, and you apply that to Y star, okay? Now, semantically, what we're doing is very strange because, Y star, this is an optimal fractional solution for the VIs, the real valuations. Right now, we have these totally fictitious pseudo-valuations, these ZIs, and it's not clear that, if you actually resolved an LP for the ZIs, you'd probably get something totally different. You wouldn't get Y star. Again, Y star was optimized for the VIs. But nevertheless, if you want, you can still apply randomized rounding to any feasible LP solution. Y star is one of them. So go ahead and do that. And what we know is that if you apply randomized rounding to a feasible LP solution, you get an integer solution which is almost as good. Right? That's what we proved. So if this constraint is satisfied, it means you have a fractional solution, Y star, which for the valuations, these pseudo valuations, the ZIs, is good. It's bigger than Z star. If you do randomized rounding, you're only going to lose a 1 minus epsilon, and you're going to get an integer solution. And that's going to, in fact, be an allocation, an integer solution, which violates this constraint. Okay? I mean, think about dividing the 1 minus epsilon here. Okay, so this fractional solution is way better than Z star. It's better than Z star divided by 1 over epsilon. You do randomized rounding, you get an integer solution, which is still strictly better than Z star. That violates this. So you just return that as your separation oracle. Okay, and that's it. That's the whole separation oracle implementation. Okay, so we don't actually, what we need from last week is just the simple idea that randomized rounding scaled down slightly does almost as good as the expectation. That's kind of the only thing we're using. So any questions about that? I hope that sort of cleared up that point. Okay. All right, so now for basically the culmination of part 2, I want to circle all the way back to where we started, which was submodular evaluations. So just to remind you, at the time, we had just sort of finished our victory lap with all the tractable special cases. We'd sort of knocked off gross substitutes. We'd seen we could, implement the VCG mechanism and so on. And we went what seemed like just a very small step beyond gross substitutes. So we have a set U of items not identical. And each VI is submodular. And this is just sort of a set theoretic version of diminishing returns. Your value for something, your marginal value for something is going down the more stuff you have. So the more you have, the less you want more stuff. Okay, so if I look at how much extra value J gives me, that's less for the bigger set than for the smaller set. And, okay, but we saw already here welfare maximization is NP hard. So that was sort of the can of worms we opened when we passed from gross substitute to submodular. We also showed that it's just an approximation problem. Welfare maximization is not that bad. All you do is run the Kelso-Crawford auction, and that already gives you a 1/2 approximation. Okay, and there's other 1/2 approximations as well. And then we ask the question, okay, well, how can we get a good approximation and also get DSIC? And I've given you no answers to that. Instead, we took these detours to multi-unit auctions and to these things with multiple copies, and we've developed our toolbox. And so now in particular, we understand MIDR mechanisms, and we're going to apply that to solve at least a special case of scenario number 6. Okay? So no full-blown solution to scenario number 6 exists. Or none is known, and I'll tell you probably a little bit tomorrow about the sense in which we think there isn't any for the full class of submodular valuations. But here's the special case that we'll be able to solve. So this is a subclass of submodular valuations called coverage valuations. And so a given valuation VI is coverage if it has the following form. So for a bidder I, there's going to be some ground set. So you could think of this as being, cities or something like that. And for each item, there corresponds a subset. Okay? So these are going to be AIJs. And by definition, the valuation of a bidder is going to be the area covered by the sets corresponding to the items that it's given. So let me give you a couple examples. So one thing is you could imagine that XI are a bunch of cities, maybe cities in the US. And items are, licenses to, broadcast something or, permission to do something else. And so AIJ could be the set of cities that a particular license enables you to reach. Okay? And your goal is to have coverage, if you like, of as many cities as possible. Okay, so you can think of these AIJs as broadcast radii. Okay? And so it doesn't do you any good if you have two different, you have permission in two different ways to broadcast to the same city. It only counts once. Okay, so given a bunch of licenses, you look at the union of everybody you can reach, and that's what you get credit for. That's your value. Or if you prefer, maybe you're a firm, and XI is a number of skills you're trying to hire, or maybe you're a sports team, and those are, positions that you need to fill. And so then basically these AIJs are going to correspond, it's going to correspond to the skills of a particular worker. Okay, so a worker maybe can do multiple skills, they cover multiple needs, and maybe you don't need more than one worker for the same thing. So you get credit for the union. Okay? So that's how you should think about coverage valuations. It's pretty easy to see that every coverage valuation is in fact submodular. So basically, what's the added value of a new person? Well, it's just the things in XI that you cover that were not covered before you got there. Okay? And so the more other stuff there was, the less new things you cover. So the less your marginal value, the bigger the set of other people that are already there. Okay? So subset of submodular valuations. Okay? Now you should, whenever you pass to a special case, you should of course argue, well, all right, but is this even still a hard problem now? Maybe this is now a subset of gross substitutes or something like that, and we already know how to solve it. Okay? But in fact, welfare maximization is actually still hard, okay, even for coverage valuations. So here's the best impossibility result known for approximating welfare with coverage valuations. So there's no polynomial time approximation. For welfare maximization, better than 1 minus 1 over E, which is roughly 63%. Okay? So I'm going to assume, so what's true in this negative result, and what I'm going to assume for the positive result is that the input is just given explicitly. Okay, so I just literally tell you what my AIJs are. Okay, and then that's the valuation. And I'm going to tell you an AIJ by just listing the elements in the AIJ. Okay. So assume the AIJs provided as explicit input. Okay. So, I mean, this certainly says it's not part of gross substitutes, or at least assuming P is different than NP, it's not part of gross substitutes, because that we can solve in polynomial time. Okay, so it's still it's a subclass of submodular which still motivates everything we've been talking about, which is when welfare maximization is NP hard, what do? How do you get DSIC approximation mechanisms? And so the point of this lecture, so this is a result by a couple former PhD students of mine, Shadandugmi and Chichi Yan, is that using a MIDR mechanism, and hence a DSIC mechanism, that gets a matching approximation guarantee. Okay? 1 minus 1 over E for coverage valuations. Okay? And so again, this is sort of the happy case where, first of all, so this says, notice this in a proximity result, this is nothing about incentives. Right? This just says, forget incentives, just polynomial time algorithms can't do better than 63%. So we're doing as well as any polynomial time algorithm, incentives are not. So that's the first piece of good news. The second piece of good news is that, as approximation algorithms go, 63% is a pretty good number. Okay? There's a lot of problems where you can't get this close to 100% in the worst case. Okay? So again, there's not tons of positive results in the DSIC approximation world, but this is another interesting one.
Are you assuming something about the complexity of Xi? How big the ground set is?
Well, I mean, not per se, because I'm just assuming it's part of the input. So, if Xi is big, you're forced to write it down, and I'm allowed to be So, in effect, the algorithm is allowed to be polynomial in the size of the Xi, whatever that may be.
And can you approximate? So, if you're given any submodular valuation, can you rewrite it as a coverage in some high enough, complicated enough Xi?
It's a good question. No. Yeah, I don't think so. I see. So, yeah, so maybe with an exponential ground set, you're thinking? That I haven't thought about. What do you think?
It seems like it.
Yeah, maybe with exponential, maybe you need maybe with an exponential size ground set. I haven't thought about that actually.
But you will involve like the size of the set somewhere.
Well, the claim is it's polynomial in the size of the input, where the input is defined to be the AIJs, which are explicit lists. Yeah, so in that sense, it has a pseudo-polynomial flavor in that sense. But that's another reason why sort of this is important. This is already, so this hardness result is for this version of the problem. Yeah. So, in the hard instances here, of course, the XIs aren't going to be ridiculously big. It's not going to be some, it's going to be a reasonable encoding of things, but yeah. Yeah, I'll have to think about that. Whether given kind of unbounded sets you can encode, what you can encode. It's a good question. Okay. Right, and I should say, so in particular, you'll notice this is a 1 minus 1 over E approximation algorithm. Right, so I haven't even, even forgetting incentives, I actually haven't told you a positive result this good. I've told you a 1/2 approximation, a 50% approximation for general submodular functions. But there were, so in 2006, there was a 1 minus 1 over E approximation, non-DSIC for coverage, and then in 2008, there's 1 minus 1 over E for general submodular functions. So prior to this, it was known you could get this without incentives. Not a lot prior to this, but prior to this, it was known you could get this. So it was clear that this would be the holy grail for an approximation mechanism. Okay. Okay. Any other questions? All right. So it's going to be an MIDR mechanism, but we're going to have to. It's not going to be one of these scaling algorithms. It's not going to be a special case of the Levy-Swamy framework. So let me just comment on why do we need to do something different. So there's a few reasons actually, but let me tell you the main reason. So what was the idea in Levy-Swamy? The idea in last lecture was, okay, you give me an approximation algorithm which I can't lift into a mechanism, but then I'll somehow smooth the approximation error over all of the inputs so that without any loss so that I can get the incentives. So I'm telling you that for this problem there are these good approximation algorithms that get 50% or 63% or whatever. So maybe we can just again do the same thing where we solve an LP and we smooth that error over everything. And then we're good to go. So why can't we do that? Okay, so let's suppose as a hypothesis that I gave you an algorithm, which let's say for every submodular valuation function got a good approximation. Let's say it got 50% for every submodular valuation, like Kelso-Crawford, okay? And that's the guarantee. Here's the problem, okay? So in Levy-Swamy, where did we actually use the existence of a good approximation algorithm? Okay, so it didn't show up until buried inside the separation oracle that we used when proving the infeasibility of the dual. Here. So we used it to say, oh, well, if we have this solution with good fractional pseudo-welfare, we'll invoke our approximation algorithm to get an integer allocation with almost as good pseudo-welfare. Here's the problem. So what instance do we invoke the algorithm on? We invoke it on the instance thinking of the ZISs as valuations, okay? And the problem is we have no control at all over what these ZISs are. Okay, remember we're just like running the ellipsoid algorithm and it's just sort of generating these ZISs for us. It's like, oh, here, deal with this, here, deal with this. And we're having to sort of parry these ZISs by feeding back violated inequalities. These ZISs, they're not going to be submodular. Okay, they need not even be monotone. They can be anything. So just having an algorithm which does well for submodular valuations, which are the valuations we care about, the VISs, totally useless once we're faced with these arbitrary ZISs that the ellipsoid algorithm gives to us. Okay? So it really doesn't seem to help having a good approximation algorithm for subclasses of valuations in this Levy-Swamy framework. You really seem to need general valuations, okay? Because the ZISs could be anything. So let me just write that. So ZISs in D2 could be anything. Okay. So approximation algorithm for special cases, not directly useful. So full disclosure, there's some other kinds of incomparabilities or reasons why this particular problem doesn't fit into their framework. For the Levy-Swamy result, they need valuations that support demand queries. The reason they needed demand queries is in the very first step. So what they start by solving the LP relaxation to get this fractional allocation, maximizing the welfare over fractional solutions. There, the separation oracle is a demand oracle. Turns out, it's actually not hard to prove, reduction from set cover. If I give you a coverage valuation, it's actually NP hard to answer a demand query. So way back when I started talking about queries, I said, value queries, pretty uncontroversial, right? You got to tell me what your value is for a set. Seems like a minimal query. Demand queries, we said, well, I said that sort of the mathematical results are more mixed, and it's more that it's natural to ask for demand queries. So here's here's a concrete example where the mathematics are mixed for demand queries. It's a pretty natural valuation class for which answering one is NP hard. Okay, so that's another reason why Levy-Swamy doesn't apply here. Okay, because these don't support those in polynomial time. That said, a value query for a coverage valuation is easy. You just enumerate through the xi's and just check, which of the xi's are contained in one of the given sets. Okay. All right. Okay. So the upshot is, all right. So Levy-Swamy doesn't seem to work. At least it's not clear how to use it. But we want to do some MIDR mechanism, and still, if you think about, as far as all the algorithms in the world, which ones seem like they might yield MIDR mechanisms, it still seems like randomized rounding is kind of the closest to it. Again, because you're doing this optimization over these fractional solutions, and the randomized rounding generates these distributions. It kind of feels like on the right track. So, but we need to go beyond scaling algorithms. Okay, if you restrict yourself to scaling algorithms, it feels like you're basically, it really is this Levy-Swamy framework. It's hard to see. They seem like more or less the same thing. So the big question then is, what else could we do other than a scaling algorithm and get a MIDR randomized rounding algorithm? That's kind of the conceptual hurdle we have to climb over. So question, how to go beyond scaling algorithms. So let me just remind you sort of the blueprint that I had in mind. So the way we're thinking about it is the VIs are fed as input to some LP solver. The LP solver generates the best fractional solution y star for the given input, the VIs. This is the input into a rounding algorithm, an oblivious rounding algorithm. R. And then that generates some distribution over allocations. And scaling algorithms were by design so that optimizing over the output of the rounding algorithm, optimizing over the distributions, was exactly the same problem as optimizing over the input to the rounding algorithm, optimizing over the LP solutions. And so the challenge, but differently, is that, you know, for most rounding algorithms, okay, so like I said, MIDR is not the kind of property you ever get accidentally. Right? If you're not designing for it, you're not going to get it. So for most R, it's just not going to be the case, as we talked about last lecture, that the optimal Y, where this is over the LP solutions, corresponds to the optimal R of Y. Okay, scaling algorithms has this property. Most rounding algorithms will not. So, and again, it's not even clear. I really don't have any ideas how you would ensure this property other than through scaling algorithms. So we need a different idea. Okay, so here's this sort of crazy idea. And it's kind of motivated, you know, by the idea. Okay, so we want an algorithm with a bunch of properties, right? So we want, you know, we're thinking MIDR because that's about the most powerful class of mechanisms we know. We want it to be, you know, run in polynomial time. We want it to have a good approximation factor. Okay, and so for what we've been doing is we're saying, well, we know how to get polynomial time and a good approximation factor, so let's try to sort of tack on MIDR somehow. Okay, and that very successfully led us to the scaling algorithm idea, which is great. But so now we're kind of stuck, right? So now let's actually go back and ask, well, you know, is there some alternative approach where, you know, MIDR is the property that seems really hard to get, like the hardest to get. So can we have some high-level approach that would guarantee the MIDR property, and then we can sort of investigate, you know, what are the conditions, extra conditions do we need to recover polynomial time and good approximation? Okay, so let's shift our focus. Rather than thinking of MIDR as an add-on to the algorithms we already have, let's actually take that as the initial constraint and then go from there. And that'll lead us to think about a very different or somewhat different kind of algorithm. So how can, you know, what would it look like, you know, so what could we do that, like, by definition would give us MIDR? So here's what we could do, okay? So the idea is, instead of optimizing, as we've been doing all along, over the LP solutions, i.e. instead of optimizing over the input to the rounding algorithm, let's optimize directly on the output of the rounding algorithm. And again, for a scaling algorithm, those are the same thing. For a non-scaling algorithm, these are different things. So instead of optimizing over these are still going to be our decision variables, but let's optimize over this objective function. So here's what I mean. So let's see if we could directly solve. Okay, so here's what we have. So we're still, you know, maximizing some notion of welfare. We still have some same decision variables as before. So it's still going to be subject to y feasible for some LP. But instead of up here writing as I've always been doing, you know, sum over I, sum over S, YIS, VIS, I'm going to write something different. I'm going to write, let's actually just sort of look ahead to the expected welfare we're going to get from the rounding algorithm if we feed in Y as input. So in other words, how do I want to write this? I want to write this like this. So expected value, so for a given choice of Y, there's some corresponding distribution, R of Y, over allocations. This is just a random allocation from the distribution, i.e. this is just the output of the rounding algorithm if you feed it input y. And I just look at the expected welfare. Okay. So relative to before, basically what I've changed is the objective function. And again, rather than measuring the quality of an LP solution y by the usual linear objective function, I'm measuring the quality of a solution y to these constraints by how good is the resulting random allocation after I apply the randomized algorithm R to it. So again, the point is to optimize directly over the output of capital R, not over the input. Another thing to notice, so this optimization is only defined with respect to a rounding algorithm, capital R. So you should think of capital R as fixed. Okay, so we fixed some algorithm that takes a linear programming solution and somehow generates randomly an allocation. R is fixed. Then this optimization problem, at least it's well defined to write it down. Okay. Okay. So in effect, optimize over the output rather than the inputs. Okay. And so I told you. So the only reason you'd ever come up with this is if you were trying to guarantee some very challenging property like MIDR. So the whole point, the whole reason we thought about this is this gives you MIDR by definition. Okay, so if so in other words, consider the allocation rule, which solves this optimization problem. Okay, thereby computing a y star, and then apply the rounding algorithm capital R to it. Okay, so therefore randomly outputting a allocation. So the claim is that allocation rule is MIDR for sure. Why? Well, so what's the range of this rule? So the range of this rule is just all output distributions of the rounding algorithm for solutions that meet the LP constraints. Okay? So the range is just, imagine any input to the rounding algorithm, imagine the corresponding distribution, and the objective function literally says, pick the best of those distributions to maximize expected welfare. Okay? So really, the definition of this objective function means it's an MIDR allocation rule. Okay? All right. So, not clear this is, this is sort of a crazy idea. Okay. Let me just point out that, all right, so like I said, this optimization problem is defined with respect to a rounding algorithm R. So let me just point out, if R happens to be a scaling algorithm, then actually this is a very normal optimization problem. Okay? And in fact, this is sort of one way you can sort of interpret the previous lecture. Okay? So scaling algorithms are the ones where this problem becomes a linear program. Okay? So if R is alpha scaling, then the objective, right? So if R is a scaling algorithm, then this is always just the expected welfare. But if it's a scaling algorithm, the expected welfare is just alpha times the LP solution value. Okay? So the objective would just be equal to alpha okay? And this was just our computation before. So when we first introduced alpha scaling algorithms, we noticed that given an LP solution y, the expected welfare of the energy allocation is the same scaled by an alpha factor. Okay? So that's just, we're plugging in that computation here. This, you'll notice, is linear. That should be just a y. This is linear in the decision variables, the y's. Okay? So this would just be a linear program if capital R is a scaling algorithm. Okay? So at least, it captures the special case that we used successfully last time. So the hope then, again, and remember, the whole point here is how do we go beyond scaling algorithms subject to MIDR? Okay? So this at least is sort of now like a concrete proposal. So we can say, okay, here's an optimization problem. No matter what capital R is, it's MIDR. So now what we want is say, for what rounding algorithms can we solve this in polynomial time? Okay? And get a good approximation. If it's a scaling algorithm, we can solve it in polynomial time. Is there anything else where we can solve this in polynomial time? Well, the first question would be, is there anything else for which this is linear? And that, it seems like that's basically only scaling algorithms. But we can actually, we can solve some nonlinear programs in polynomial time as well, right? If this is a concave function in y, then it's still a tractable problem, right? So concave maximization subject to linear constraints, that's something we can do. So a pathway to go beyond scaling algorithms is to say for which rounding algorithms R is this objective function concave and the decision variable is y. Okay, so hope is that this optimization problem remains tractable for some non-scalar R's. Of course, we're also hoping R gives us a good approximation. Okay? E.g., if objective function is concave. Okay? So that's sort of the dream. Okay? All right. So where I want you to be is I want you to agree that if star is tractable, then we have an MIDR mechanism. Namely, you solve it, you get the y, you apply the rounding algorithm capital R to it. Okay? That's an MIDR allocation rule. So what you should be wondering is, are there any interesting non-scalar capital R's? All right, so let me show you a rounding algorithm, a capital R, which doesn't work, but it will be very instructive in the way it doesn't work. Okay? And I guess I should say for what I've said up till now, this also has nothing to do with the valuations. Okay? So it's just always true that this will be MIDR, whatever the valuations, whatever the rounding algorithm capital R. So really what we're going to eventually come up with is we're going to come up with joint assumptions on, first of all, the valuations, namely the assumption that they're coverage valuations. And then also we're going to judiciously choose this rounding algorithm capital R so that we do get concavity and a good approximation. Okay, so that's what's eventually going to happen. All right, so non-example. All right, so I'm going to use a simpler linear program than we've been using so far. Okay, and that's sort of well motivated because if I want to prove that the objective function is concave in the decision variables, kind of the fewer decision variables I have, the better. Okay. So I'm going to switch. So the linear programming constraints will be very simple. There'll just be a Yij for bidder I getting an item j, and we're just going to say that no item can be allocated more than once. That'll be it. Okay? So Yij non-negative for all ij, and then also each get allocated at most once. So this is we haven't really seen something this simple since the unit demand days. And actually this is even simpler because I've dropped the constraint that every bidder gets at most one good because they're not unit demand, so that wouldn't make sense. Okay? So our set of decision variables and the constraints are going to be simple. Okay, so that's nice. Now consider the following rounding algorithm R. Okay, we're just going to do the simplest randomized rounding imaginable. Okay, so remember, a rounding algorithm, it just takes as input some y's and it outputs randomly an allocation. So if you give me Yij's that satisfy these properties, just going to do randomized rounding. Okay, look at each item j independently. I'll think of the Yij's as a probability distribution, and Yij gets j with probability I gets j with probability Yij. Okay. Any leftover probability, if this is less than 1, it just goes to nobody. independently for each good j, assign j according to the probability distribution induced by the bidders. Again, leftover probability, it just winds up unassigned. Okay? So this is a particular proposal for capital R. We're going to assume that they're coverage valuations. And what I want to investigate is whether or not our objective function, okay, the expected welfare after the rounding algorithm, after that rounding algorithm, whether or not that expected welfare is concave in those decision variables, the y's. Okay? All right. So just a preliminary observation, sort of a sanity check. If you think about it for a second, this could never work. By which I mean there's no way that this rounding algorithm could give us a concave objective function. Let me explain why. So notice, this goes back to a comment I made last lecture when I was talking about the imperfect analogy. I said, why do MIDR? Why allow distributions? Well, maybe it gives us tractability, like linear programs give us tractability. But then I pointed out this distinction that linear programs, you get sort of extra stuff. Right? You optimize and it's easier, but then you get things that are sort of even better than integer solutions. But if you're dealing with distributions, you never get something that's better than all the integer solutions, right? Because a distribution is dominated by the best solution in its support. So we're going to see that come up here. So think about this rounding algorithm. What if I fed this rounding algorithm capital R? What if I fed it an integer solution, a 0-1 solution? So like the y's just say, the first item goes to bidder 3, the second item goes to bidder 5, the third item goes to bidder 1. What's the rounding algorithm going to do? Just going to be like, okay, you already know what you want. What do you need me for, right? So R of y is just going to be y. I mean, it's sort of an abusive notation, but basically, a 0-1 vector, is a characteristic vector for an allocation, and this thing will be a point mass at that allocation. All right, so what would it mean to be, so now think about being MIDR, right? So that means, so you need to look at all the distributions in your range. So this says, in particular, every point mass is in the range of this rounding algorithm, right? You give me an allocation, an integer allocation. There's a corresponding 0-1 vector y. If I feed it into R, I get it right back. So every single allocation, every point mass is in the range. So if you're going to optimize over this range, you have to, in particular, optimize over all of the integer allocations. And the whole point was to attack problems for which that's a hard problem using MIDR. Okay, so this can't work. There's no way that a rounding algorithm that leaves integer solutions untouched could possibly be computationally tractable unless p equals np. Okay? So we know this is doomed to fail, okay, because the point masses survive in the range. But it's instructive to still try to prove it concave, even though we know it's not, to see where the concavity proof fails. It's going to actually lead us quite directly to something else which is concave. Okay? All right. So again, the point here is optimizing over the R of y's as hard as the original problem. Okay, but let's try to prove it's concave anyways. All right, so is it clear what I'm about to try to do? So we have this space of n times m decision variables, yij, for every bidder and every item. Okay, so this is kind of the feasible region we're dealing with. We're looking at this objective function. So remember what this is. This is the expected welfare after the randomized rounding algorithm gets applied to y. So this is some real valued function on the y's. And we can ask whether or not this is concave for this particular rounding algorithm R. Okay. All right. So, proof attempt. All right, so first observation, so we want to prove this is concave, okay? Sum of concave functions is concave. So let's just try to prove this separately for each bit or I. Okay, that's sufficient. So enough to show that for all I. So I'm going to abuse notation here a little bit. So you can remember y, it's just these yij's. This is the distribution over allocations. That has some set si going to I. Okay? So this is just like what bit or I gets from the randomized rounding algorithm. So enough to show that this is concave in y. Okay? Good. So now, using the assumption that the valuations are coverage valuations, I can simplify this concavity problem even further. Okay? So, let me just remind you, so what's the picture you should have? So we have this ground set. Items correspond to these subsets, and valuations are just the union, the area. I guess actually one comment I forgot to make. So everything in the lecture today extends with no change if these guys have weights also. So if these are cities and you want to weight it by population, no problem. Okay, it would be extra notation and just no extra complications. But just think about the basic case where we're looking at the cardinality of the union. All right, so we're looking at the expected value, the expected size of the union of the sets that I gets. So let's just think about it from the perspective of some element. So think of it from the perspective of just like San Francisco, right? So what's the probability that San Francisco contributes 1 to this valuation? Well, it's the probability that this guy gets any of the items that include San Francisco in it, okay? So let's just write that out. So since this is just the union, the cardinality of the union, we can write this as a sum over the ground set xi of the probability that each element of the ground set winds up in that union. Okay? So sum over everything that might contribute to the union, and the probability, where again the probability is with respect to the coin flips in the rounding algorithm applied to y, that A winds up in yeah. Okay. So we use linear of expectation once to say concavity of the welfare just boils down to concavity of each individual bidder, and then for an individual bidder, we just say, oh, well, again, you know, by this summation. So we're trying to prove that this whole thing is concave, and it's enough to just prove that each constituent term. So want this to be concave in y. Okay? And this is starting to look like terms that we can really get our hands on. I can understand well. Okay? But again, so a sufficient condition for the objective function to be concave and therefore total tractability is that this expression, this probability is a concave function of the variables y. Okay? All right. So far the proof is working. This is looking great, right? Like coverage valuations have been really useful. Yeah. Okay? So what is this? So let's just write this out. So for a given, okay, so we've fixed bidder I, and we've fixed an element A of its ground set x sub I. Okay, something that might contribute a unit to its value. So as a function of y, what is the probability that A contributes to I? Okay. So remember what this rounding algorithm capital R is. It's very simple. Given the yij's, okay, it just says, okay, I gets item j with probability, you know, yij. That's it. So what's the probability that little a contributes 1 to i's value? Well, how could it not contribute 1 to i's value? It would have to be that for every single set, every single aij that contains little a, I doesn't get it. Okay? So this is just 1 minus the probability that it doesn't get little a. And so for that to happen, for every single set that contains little a, so if you like every single item that covers San Francisco, it has to be that, you don't get it. And that happens with probability 1 minus Yij. Okay? So this is exact. So our big high-level goal, proving this thing concave, reduces to proving that this is a concave function of the y's. Or if you like, that this is a convex function of the y's. Which is not. Okay? So why not? So what does concave mean, right? So concave is this way, right? So chords are underneath the graph. So it basically means if you think about taking the average of 2 points or taking the function value, if you take the function values first and then you average, that's like the chord, so you get something lower. If you average first and then take the function value, that's like the graph, that's higher. So let's look at this. Look at this function. So like imagine, say you had a y vector where exactly one of those was a 1 and the rest were zeros. Okay, so Yij was equal to 1 for one of them and the rest were zeros. Well, if you have Yij equal to 1, right, then this whole thing's going to evaluate to 1. The product will be 0, you'll have 1. But think about averaging two different y vectors, each of which have exactly 1, 1 and the rest zeros. You're going to get a vector that has all zeros except for 2 1/2. And then those halves are going to multiply and give you a 1/4 there. And this will give you a 3/4. Okay? So you averaged two things that had value 1. You got something that had functional value 3/4. So that's a violation of concavity. Okay? All right. So, but actually, we got pretty far in this proof. And we knew it wasn't going to work in the first place. So, can we fix it? All right, what does fixing it mean? Fixing it means changing the rounding algorithm capital R. Okay, doing something a little less obvious in the rounding. Okay, so that we get concavity. So, all right, so if it weren't good, so what would be kind of like the next simplest rounding algorithm we could possibly do? Well, let's remember that, let's remember the very initial cautionary tale. That any rounding algorithm that maps integer solutions just back to themselves is doomed to fail. Okay? So in particular, if you get an LP solution which says Yij equals 1, you actually are, you really should not be giving j to I with probability 1. You have to do something else. So probably the first thing you think about is okay, well, let's just kind of scale down the probabilities a little bit. Okay, let's allocate with probabilities less than Yij. I don't know what, but something smaller than Yij. So, simplest possible fix. So use probabilities. So let me just parameterize it. And we'll sort of take stock and figure out what we want, okay? So let's use probabilities f of Yij's instead of Yij's. By which I mean, our rounding algorithm will continue to be exactly this one, except we're going to replace the Yij's with some function of Yij. Okay, think of it as like a scaling down operation, which we know something like that has to be necessary. Okay? And so, right, good. So if we were going to somehow transform these Yij's, scale them down, what properties do we want? Well, so what sort of would be can we sort of think about what f might look like? All right, so we're thinking f of Yij should probably be maybe at most Yij. Two reasons. One is the one I've been harping on, which is, again, we can't just sort of deterministically, follow an integer solution. So that says probability should go down. The other thing to remember is we do need sort of a well-defined rounding procedure at the end of the day, right? So we're using the fact that for a given item j, the sum of the yij's was at most 1. So it made sense to say give it to a random bidder according to the yij's. So we better preserve the property that, the sum of our allocation probabilities is at most 1 for this to make sense. So that's another reason why it seems like f of yij should only be less than yij. That said, given that we want an approximation ratio, probably we don't want f of yij to be too much less, okay? Because maybe we're losing all our value. So let's just say, but not too much. In fact, if you think about this argument, so what did I say at the very beginning of the lecture? So we're talking about coverage valuations, and I said, well, you should be skeptical. Have I made the problem trivial? Have I made it too easy? And then I stated this hardness result, which is actually you can't do better than 1 minus 1 over e for these coverage valuations. So if you think about combining that fact with this idea that you have to scale down, it actually suggests about what f of 1 should look like. The fact that you can't do better than 63%, it actually means that if I give you an integer solution, you better not even always scale everything down just by like 65%. Okay? Because even then you're going to be optimizing better than what the NP hardness says should be possible. So this is now starting to get a little more of a guess. But judicious guesses is an important part of research. So the hardness result, I guess I would say you just gotta keep your eye out for the clues, is what I would say. So the fact that it was hard to within 1 minus 1 over e says, well, maybe, so that means in particular giving integer solutions we have to lose a 1 minus 1 over e. And the simplest way to imagine where you'd kind of lose that welfare is just by scaling down. So this suggests that at least in this sort of simplest thing that could possibly work, where you use the same function f to manipulate all these probabilities, it suggests that actually all the way out at 1, where the LP is telling you to definitely give j to I, maybe you shouldn't give it to, you shouldn't give j to I with probability more than 1 minus 1 over e. That's a guess you might have. All right. Now, but then of course the other thing, the whole reason we're in this mess is because this thing isn't concave, right? So actually these are just sort of side goals. Really what we want is we want that to be concave, okay? I probably should have listed that as number 1, actually. So 3, so let me just now write this way. Okay? All right, so let me give that a better name. But actually, let's just try to think about, what's the simplest f that would satisfy 1 and 2, even? Yeah, so if at 1, you want it to be like 1 minus 1 over e, it's kind of tempting to just set f of y to be 1 minus e to the minus y, right? Even ignoring 3, it seems like that's the simplest thing that might give 1 and 2. So guess f of yj will define to be 1 minus e to the minus yij. So what does that look like? So if this is f of y equal y, 0, 1, 1, then this looks like this. Okay, where this curve is always, the 1 minus e to the minus y curve is always at most this one, sort of tailing off. So we have for yij in 0, 1, we have f of yij. It does satisfy 1, so it's always going to be at most yij, and then the furthest it is ever away is at the rightmost point. Okay? All right, so that certainly satisfies 1 and 2. What about 3? So actually, even though sort of concavity was the whole point of this exercise, and we didn't even use concavity to guide us in guessing what f should look like, we just get it anyways. It just works, just totally works. Okay, it's kind of magic. So, so what is this now? What does star star evaluate to? So these just become e to the minus yij. We're taking the product, so it just becomes the sum of the yij's up in the exponent. Okay? Okay. Which is concave. So concavity, it just boils down to this part being convex and the exponential function is convex. Or if you prefer, you could look at the Hessian, and the Hessian is just going to be sort of a single block of non-zeros, all of which are equal to exactly the same constant, which is negative. So it's a negative semi-definite Hessian. Okay? But basically, it doesn't get much more convex than the exponential function. So it totally works. Okay? All right. So to review, okay, so what have we done? All right. So we've done something where, so we have a rounding algorithm now, which has definitely 2 of the 3 properties that we want. So there's still one more property I have to prove to you. First, let me just make sure it's totally clear what the allocation rule and what the rounding algorithm is. Actually, let me write this down. Yeah. Okay. So what have we done? Okay. So first of all, what's the rounding algorithm that we're proposing? It used to be this one, where you just do randomized rounding with respect to the yij's. Now it's just you do randomized rounding with respect to 1 minus e to the minus yij's. These are at most yij, and the sum of the yij's are at most 1 for an item j, so this is well defined. There's going to be this residual probability, more than before, that an item is allocated to nobody, so be it. Okay? So that's the rounding algorithm. Now, what's the allocation rule? The allocation rule is just solve the following problem. So maximize over y. So again, this is sort of given the VIs, coverage valuations explicitly through their sets, the AIJs. So remember what we had up here before is we had the expected welfare post-rounding. Okay? That's how we got this expression in the first place. Right? So this was just the welfare of a particular bidder post-rounding. That became this using the coverage valuation assumption, and then that became this, with a short thought experiment. And now I've told you what the F is. So just to recap, what's the contribution of each bidder I? Well, you just iterate over the elements in its ground set, and you look at the probability that it gets some item j, whose aij includes this little guy a. Okay? And that is just this term. Okay? And then subject to sum over yij for all j, yij non-negative. Okay, so the allocation rule is write this down, solve it, get the best y, okay, some y star, run this randomized rounding algorithm, so do independent randomized rounding with respect to the f of yij's, and that's it. It's the whole allocation rule. Okay? As we've seen, anything of this flavor by definition is MIDR. MIDR, that's by definition the objective function. We chose the rounding probabilities judiciously to force the objective function value to be concave. So this is a concave maximization problem subject to linear inequalities. So modulo some sort of technical annoyances that I'm not going to bore you with in lecture, this can be solved in polynomial time, for example, using the ellipsoid algorithm. Okay? So we wanted three things. We wanted MIDR, so we get the incentive properties. We've got it. We wanted computational tractability. We've got the concavity, so we've got the tractability. And then the third thing, which I still need to prove to you, is the approximation guarantee. I have to prove to you that actually, at the end of the day, when we solve for y star and we run the rounding algorithm, we get a good allocation. Okay, we don't actually know that. There's sort of hope, right, because we haven't actually tweaked the yij's too much, but I do owe you a short proof for that. Okay? Questions? Yeah.
This allocation rule might give a DSIC mechanism, but it's kind of unfair.
In what sense?
Because it penalizes people who want a lot of stuff a lot more than it penalizes people who don't want a lot. So alpha scaling penalizes everyone the same.
I see what you're saying. So, I mean, with respect to the y's, I mean, so the quest, I mean, so penalized in, so you got to remember, I mean, you know, like the LP solution, the y's, this might be unrealizable. Right, so it's a little bit unfair to kind of say, oh, you're doing so much worse than the LP solution, because the LP solution doesn't necessarily represent some realizable reality, right? So it could just be that, you know, right, so when you solve for a fractional solution, in general you get stuff that's better than the integer solution. So it could just be that, like, you're the bidder who's the reason why the fractional solution is so fictitiously large. So then you don't really have a right to complain when you say, oh, but the LP solution says I should get so much, you know, if there's no integer allocations that give you that much. So, I mean, there are probably cases where what you're saying is true, but it's not, I still don't really like using the y's as a benchmark. I think that's sort of unreasonable. Yeah, it's a good comment though. Other questions? Okay. So the approximation. All right, so I forgot to say, right. So an output, allocation, omega sampled from the rounding algorithm, this rounding algorithm applied to the optimal solution y star. Okay. All right, so the claim is, so the final claim is that this is a 63% approximation in expectation. Okay. All right, so one thing that's cool about these MIR and MIDR allocation rules, and we did the same thing last week with multi-unit auctions, is all I have to do is exhibit some feasible solution with good expected welfare. Because remember, MIDR, what does it do by definition? Of all the feasible solutions, it picks the one that's best for the bidder. Okay, so if I show you one good one, it does at least as well. So need to exhibit some feasible y hat such that expected welfare in R of y hat at least 1 minus 1 over e times opt. And it's quite straightforward which one we should try. So basically, you know, there is some optimal allocation. It's natural to just say, well, you know, what if we just kind of fed into our rounding algorithm that we want the optimal allocation? Okay, what's it going to do? So just set yij to be equal to 1 if in the optimal allocation I gets j, 0 otherwise. So these were exactly the kinds of y's that were getting us in trouble before, right? Because it did nothing. It just handed us back the optimal allocation. So now that we fixed that, we just have to show we're not losing too much. Okay? So claim is that the expected welfare of your favorite bidder, bidder I, is at least 1 minus 1 over e. So again, expected with respect to the output of the rounding algorithm, if you feed it in this very strong hint about what how items should be allocated, it will get a 1 minus 1 over refraction of that welfare it gets in this optimal allocation. Okay. And this is not hard to prove. It does rely on the submodularity of the valuations. It does not need to be coverage valuations, but you do need some assumption on the valuations for this to be true. So proof. So here's how I want you to think about this. So suppose in the optimal allocation, MIDR I gets some L items, okay? And what I want to do is I want to add these L items one at a time, okay, in parallel in sort of two worlds, right? So in the first world, it's just where there's no randomized algorithm. Okay, so there's this optimal allocation, these L goods, it gets good 1, then good 2, then good 3, then good 4, and I track the increases in I's valuation. Okay, so each successive good gives it some marginal value, and I just track those numbers. On the other hand, I imagine trying in this sort of randomized rounding world to give MIDR I these same L items in sequence. But each time I try to give it an item, there's a 1 over e chance that basically the item goes poof, okay, and they don't get it. Okay? So, a little more formally, so the high level idea is basically, okay, so I give, over here, I give the items to the bidders one at a time, and this goes up by 10, then it goes up by 12, then it goes up by 3, then it goes up by 5, whatever. Over here, with a 1 minus 1 over e probability, you actually are getting the good, because f of 1 equals 1 minus 1 over e. So the difference between the two worlds is, over here, you have the entire prefix of items, right? So if we're doing item 11, you already have the first 10 items over here. Over here, you have some subset of the first 10 items, the ones that didn't go poof, okay? But it's submodular, so the marginal value of a new item is only going to be higher on the left-hand side if you have a strict subset of what you have on the right-hand side. Okay, so that's why it's true. So let Tj be the first j items of S star I, ordered in some arbitrary way. Then, so again, so just to say it explicitly, with respect to a 0, 1 vector, right? So basically, there's no chance I get any item outside of S star I, and there's a 1 minus 1 over e independent chance that I get each item inside S star I. Okay, so put differently, what is Si? It's just the result of the following random experiment. For each good here, I flip a coin with 1 over e probability, I delete it. With 1 minus 1 over e probability, I keep it, and then you get what's left on the table. Okay, that's how you can generate a distribution of SIs from S star I. So, again, just sort of thinking about acquiring the items one at a time. So I look at the contribution to the welfare of the jth item. So that should be j. So what's the expected contribution of the jth item to I's welfare? Well, it's the probability that you get it at all times the expected added value of j, given the subset of the first j minus 1 items that you got in this random experiment. So for an item in S star I, this is exactly equal to 1 minus 1 over e. This is going to be the difference between, some subset of the first j items plus j and just that subset. So this is by submodularity, at least the marginal value with respect to the full set. Okay? So taking the 1 minus 1 over e out, we just get a sum over the items in the optimal bundle of the successive added values, successive marginal values, which is just your value for the full optimal bundle. Okay? And so again, submodularity is used crucially in this part. So if you didn't get some of the items in the past, it only increases your marginal value for the current item j under consideration. So that's the third property. You do, in fact, get a 1 minus EU over approximation. Okay. Any questions? Right, so the mechanisms in this part two are obviously very complicated. They're the most complicated ones that we'll see in the quarter. It sort of, befits the fact that we're actually, despite being not much past gross substitutes, we're at what seems to be the frontier of tractability for DSIC approximation. So to get this far, you have to work very hard, and I'll open next week with some comments about how going any farther seems in effect impossible. And so in part 3 and part 4 of the class, the plan will be to look at weaker notions of implementation, look at implementations in undominated strategies. We'll start talking about Bayes-Nash implementations. And the incentive guarantees won't be as strong, but there'll be a big payoff both in the variety of problems we get strong guarantees for and for the relative simplicity of the mechanisms that give us those guarantees. So don't forget there's a bonus lecture on Friday for those of you that are interested. So 12:50 to 2:05. On Gates 359. The goal is to understand gross substitutes through the lens of greedy algorithms. And then next week, I'll see you back on Wednesday for part 3.